Welcome to today's student revision webinar, Exponential and Logarithmic Functions, brought to you by Texas Instruments. My name is Frank Moyer, and today what I'm aiming to do is to look at some key properties and features of exponential functions and their graphs, some modelling applications of these functions, the definition of a logarithm, and also features of the graphs of logarithmic functions, and if we have time, we'll have a look at solution of indicial and log equations. Okay, so let's make a start. So exponential functions, so they are functions of the form f of x equal a to the x, where a is a positive number other than 1. Obviously, 1 to any power is equal to 1, so the graph of y equals 1 to the x isn't a terribly interesting one. But any other positive number to the power of x is an exponential function. So let's start looking at these graphs. So let's start off with 2 to the x. Just a few things. Sometimes it's useful to get a grid. So one of the questions that students often ask is, can I get a grid? And yes, you can. One of the ways you can do that, there's multiple ways of doing that. My preferred way is to get the context menu. So you just have your cursor anywhere in the empty space, and the context menu is control menu, which is the equivalent of a right click on a Windows application, and under hide show, you'll see that you can either show a dot grid or a lined grid, and that can be quite useful. Now, the other thing I'm interested in here is looking at other exponential functions. So what about 3 to the x, 4 to the x? So 3 to the x we see is similar but steeper, as you'd expect, because if you're going up in powers of 3, you're going 3, 9, 27, 81. It's obviously going to rise faster than powers of 2, 2, 4, 8, 16, and so on. Powers of 4 steeper again, powers of 10 even steeper. Now, the other thing I'm interested in is you'll notice that all of those functions all cross the y-axis at y equals 1 because any non-zero number to the power of 0 is 1. Now, I wonder what the gradient of the tangent is at that point. Now, you can add a tangent by going to menu, and under geometry, you've got points and lines, and you actually do have tangent that you can choose. You see that little tool, that little icon at the top there indicating that you can select a tangent. So I can put a tangent there. I'll escape out of that tangent tool, and I can see that the gradient is roughly 0.69 because the equation is y equals 0.69 x plus 1. Use the measurement. So if I go to menu, geometry, measurement, one of the things I can measure is slope. So I can also measure the slope, and I can see the slope there. Now, if I do the same thing to y equals 3 to the x, the slope is 1.1. So somewhere between y equals 2 to the x and y equals 3 to the x, the slope at that point must be exactly 1. So I've set this up so that I've got y equals a to the x, and I can use this slider to control the value of a. And over here I'm measuring the slope or gradient of the tangent at the point 0, 1. So I slide that across, and at a equal to 2.7, I see that it's just under 1, 2.8 just over 1. So somewhere between 2.7 and 2.8, I'll try 0.72. I can see that the gradient is 1. Now, this particular value of A is a very special value. It's called Euler's number. So Euler's number has the symbol E. It's one of those numbers like pi, which is a transcendental number, a number that you cannot obtain by solving a polynomial equation. And you can't just use E from your keyboard to obtain that number. You can go to the pi button. The pi button is just above the comma button, and if you see E there, and if you then press the Control Enter, see that the rational approximation to Euler's number is about 2.71828, and so on. If I wanted more decimal places, I can see it there. The other place you can get E, you can of course go to the button above the open bracket. That gives you E to the whatever you want to enter there. So you could put in an X or you can put in a 1. And if I do Control Enter, I can see that I get the same thing. Okay, so this Euler's number is a very special number because it arises naturally when you're studying things such as compound interest, for example. It's one of those numbers that arises naturally. So we might call that the natural exponential function. And when it comes to the logarithm of that base, it's the natural logarithm. Okay, so here I've got e to the x, and I can see that as I change the value of a, when a comes to about 2.7, it's pretty much e to the x. It gets very, very close to e to the x. If I go beyond 2.7, I can see that, no, doesn't work. And when you look at the calculus of exponential functions, you'll understand the significance of why the gradient is 1 there and why that's so important. Okay, so the domain and range of exponential functions. So as we saw there, the domain is always R and the range is positive reals. So if I have a function with a rule like 2 to the power of x plus 1 minus 3, it's defined over its maximal domain, write down the domain and range of f. It's a sort of question that often is asked in exams. So if I have, here I've got the graph of 2 to the power of x, and on the same page I'll have y equals 2 to the x plus 1 minus 3. So I can see that there's been a shift of 1 unit to the left in going from 2 to the x to 2 to the x plus 1. However, that's not going to change the domain, because if I'm going from, if the domain of e to the 2 to the x is negative infinity to infinity, negative infinity minus 1 is still negative infinity. Infinity minus 1 is still infinity. So that's not going to change. The domain is still going to be R. However, obviously the range, there's been a shift 3 down. So the asymptote is no longer going to be the x-axis or y equals 0. It's now going to be y equals negative 3. So to get the range, you really do need to look at the graphs, whereas there is, as in the previous webinar, you saw that Haley showed the domain function. There is no equivalent range function. You really do need to look at the graph and use that to help determine the range. Okay, so that's the domain and range. Now, in yesterday's webinar, I looked at transformations of algebraic functions such as y equals root x. Now, for exponential functions, the same sort of principles apply. So I've got y equals e to the x, where I now know what e is. It's that special number around about 2.718, whatever. And I've got a point P on the graph, and I reflect that point P in the y-axis, and there's the reflection P dashed. So what I'm going to do is get a trace of the point P dash, and I'll animate the point, and I can see the effect of reflecting the point P in the y-axis. And I can see that the corresponding graph that passes through all those points is e to the negative x. So e to the negative x, or in fact a to the negative x in general, is a reflection of the original graph in the y-axis. Similarly, if I do the same sort of thing, this time reflecting in the y-axis, I can see reflecting in the x-axis, I can see that the path that I'm going to get there. So we'll just get a trace. Whoops, I traced the wrong one. Never mind. Oh, there we go. So you can see that that goes through all the points. So when I reflect in the x-axis, it's going to be negative e to the x, or if the original graph was y equals a to the x, it would be y equals negative e to the x. And if I reflect in both axes, negative e to the minus x. Now, sometimes there are questions about addition of functions. So what about if you're asked for the graph of y equals e to the x plus e to the negative x? It's just a matter of adding the two graphs together. So, for example, along the y-axis, each of the graphs has got a y value of 1. 1 plus 1 is 2, so it's obviously going to cut at 2. And we can see that it's going to get closer and closer to e to the x as x approaches infinity, and closer and closer to e to the negative x when x approaches negative infinity. And we can do the same with the graphs at the bottom. Okay, so they are the graphs. What about some problems? Typically, you might get a problem where you've got an exponential function such as the electrical charge C units stored by an electronic component at time t seconds is modelled by this function C of t is 2000 times 1.2 to the power of t, where t equals 0. Determine the initial charge on the component. Determine the time taken for the amount to double, and give the answer correct to 4 decimal places. So here we're not after an exact answer, and in modelling questions you usually are not after an exact answer, because if you're measuring something, you can't measure something like the square root of 3 kilograms, for example. You need a rational approximation. And if the rule is written using the E instead of 1.2 as the base, then find the value of K. All right, so initial charge. Initial means that time equals 0. So start off by defining the function. Now, when you're defining the function, as Haley showed in the previous webinar, it's useful to use the assign. You can go through menu and go and find define, but the assign, which is Control and the template button just under the delete button, is much quicker. And I need C of 0, and not surprisingly, it's 2000. Now, if I want to do the graph, and this was shown in the previous webinar as well, if I've already defined in terms of C of t, I don't have to type in the graph, the rule of the function again using x in a graphs page, what I can do is just enter c of x, and c of x will have the same effect because wherever you had t, it's been replaced by x. Now, often you'll do that in these modelling questions and nothing happens, and that's, of course, because the scale is all wrong. Now, a quick way of changing the scale. Now, if the initial value is 2,000, you're going to want a fairly large value at the top, perhaps somewhere around 10,000. So you can just go up to the top number there, just touch it, press enter once to select it, enter again to make it editable, change that to 10,000, and bingo, I've got the graph. So that's just a quick way of changing your window settings rather than having to go in through window and you can't really see things interactively. Okay, back to, sorry. Okay, so determine the time taken for the charge to double. So if it's doubled, I'm going from 2,000 to 4,000. So it's just solving 4,000. And I guess an answer with the default number of decimal places. Now, students often make mistakes when rounding. Now, with TI-Nspire, there's really no reason for doing that because for getting the rounding wrong, because there actually is a round command. If you go to the catalogue, which is the open book symbol, and if you press R, it takes you to the top of the R. If you press S, it takes you to the top of the S. So if you go up to back to round, down the bottom there, you'll see the syntax as well. So over here, it shows you what the syntax is. Expression followed, comma, the number of digits. So I can select round and just go up to there. So just click upwards, press enter. I want that to 4 decimal places, and I don't want the T there, so I'd better edit that to get the T out. And it's correct to 4 decimal places. Just be careful, though. If you were to do that to 2 decimal places, it doesn't show the 0. But, of course, you should realise that the answer that is required, should the question ask for an answer correct to 2 decimal places, in that case it would have to be 3.80. So that's the only thing you need to be careful of when you're using the round command. Okay, well, I might leave it there for exponentials and move on to logarithms. So a logarithm is just another name for an index. So for example, if I have 10 squared, we know that equals 100. 2 is the index. It's also the logarithm with a base of 10 that gives an answer of 100. All right, so I can rewrite 10 squared equals 100 as 2 is the logarithm with a base of 10 that gives the answer of 100. Or if I generalize that to any base a to the y, if a to the y equals x, then y is the log to the base a of x. Of course, the proviso is that a and x have to be positive and a cannot equal 1. Now, logarithm templates. So where can I get logarithms? Well, it depends which logarithm you want. If you want the natural logarithm, logarithm to the base e, then you can go Control and then the e to the x button. That's log there. So if I want to get a rational approximation to that, and our n is in fact correct mathematical notation. It is not calculated syntax. It is correct. Well, it is calculated syntax as well, but it's also correct mathematical notation. The other place you can get if the logarithm is the template button just below the delete, and you'll see log there, and you can enter the base you like. So you could enter E there if you wanted to, but of course, why would you? If you wanted base E, of course, don't forget it can't be any E. It's got to be the E that you get from the pi template. Right? It does the same thing. If I wanted a different base, for example, to the base 2, all right. So we know where the template's located. We know that log to the base E, it's better to use the natural log template. All right, now I'm going to have a look at the inverse function to y equals 2 to the x. So I've done something similar to what I did earlier. I've got a point P on the graph, except this time instead of reflecting the point P in an axis, I'm reflecting it in the line y equals x. So all my x and y values are going to be swapped over. Now I'll get a trace of that, and I'll animate. And I see the trace that I get after doing that reflection. Now, to see what that function might be, one of the things I could say, now if the original function is y equals e to the x, then the inverse must be y equals 2 to the x, so x equals 2 to the y. Now I can enter that relation. If I hit the back arrow, you'll see there that if I go to number 6, I can enter a relation. And the relation that I'm going to enter is x equals 2 to the power of y. So I've swapped the x and the y. And we see that that certainly works. Okay? But if I go back to the definition, by definition, if a to the y equals x, then y is log to the base a of x. So in this particular case, if x is equal to 2 to the y, that's the same as log to the base 2 of x. In other words, if I graph y equals log to the base 2 of x, it too goes through all of those points. Right, so I can see that e to the x and log to the base 2 of x are inverses of each other. Okay. Now, the same thing, of course, works with a logarithm of any base, in particular with the natural logarithm, which is the most useful in practical terms. All right, so I've done the same sort of thing, except this time I've got y equals e to the x instead of 2 to the x. And I can see that log to the base e, or the natural logarithm of x, goes through all of those points. Okay. Now, the domain and range of the log function. As we saw, the exponential and logs are inverses of each other. So all we're really doing is swapping the domain and range. So the domain of y equals a to the x is r, so that becomes the range of the log function. And the range and domain are obviously reversed, so that the domain of the log function is positive reals, or 0 to infinity. Now, for There's a whole lot of logarithm facts, and I've got these on the worksheet that you can download from the student blog. And you need to know these, of course, for exam 1, where you're doing, you might have to solve logarithm problems by hand. For exam 2, then it's really quite easy to solve these problems because the TI-Nspire does it very, very nicely. So, for example, if I want to determine the value of x that satisfies that equation, I can do it by hand. I can use, and this is what I would have to do if it was in exam 1. I'd have to use the logarithm facts, and I'd come up with the answer x equals 3 on 2. On Nspire, it's just using the solve command. And of course, because it's log to the base e, which is what you're most likely to get in the exam, you would use ln rather than going through the other log template. And bingo, you get it in one go. Simple. You just need to be a bit careful with equivalent expressions for logarithms. So, for example, in this question, find the x-coordinate of the point where the graph of that function y equals 2 to the negative x plus 2 minus 3 intersects the x-axis. So if I do that by hand, I can come up with a couple of answers. It's either negative 1 minus log to the base 2 of 3, or I can simplify that further to negative log to the base 2 of 6. If I do that, and if it's a multiple choice question, the question might say negative log to the base 2 of 6 as as the correct answer. But if you solve that using the calculator, it gives you this answer: x equals negative natural log of 6 divided by natural log of 2. So is that the same or different? Well, you can use Nspire to check whether answers are equivalent. So I can go to that answer. I don't want the x there, but I want to know, is that the same as log to the base 2, a negative log to the base 2 of 6. So I'll go to the template, log to the base 2 of 6, and it returns true. So you just need to be aware that the calculator always gives answers in terms of the natural logarithm. And that may not be the answer you get doing it by hand, but you can use the calculator itself to check whether the questions are equivalent. Whether the expressions are equivalent. Okay, so that's very powerful, using the true, returning a true to verify that answers are the same. Now, sometimes when you do a log equation, you get a quotient symbol. Now, there was a question very similar to this. So if this log expression equals 0, then which of those is correct? There was a question similar to this a couple of years ago on the VCAA Northern Hemisphere exam. And it's one that you think, oh, well, the calculator will give me the answer. Well, sort of. So it gives you two answers, and it comes with a warning, questionable solution. So what's the correct answer? Is it the first one? Is it the second one? Or is it both? Well, there you have to consider the fact that because x and p are both the arguments of logarithms, they both must be positive. So the answer has to be, you have to reject the first one, because if p is positive, then clearly this top line here is negative. So the answer has to be the second one. So just be aware that sometimes solutions that you get with the calculator come with that warning signal, and you have to use a bit of common sense to decide which of the answers is correct or if they're both correct. All right, so I think we've come to 4:30. So that's the end of my webinar. So thank you very much for your attendance and enjoy the rest of your day.